Proof of the integral test. We have already seen the basic idea behind the proof of the integral test in figures 1 and 2 for the series to sum from 1 over n squared and the sum from 1 over the square root of n. For the general series to sum from sum of a sub n, look at figures 5 and 6. The area of the first shaded rectangle in figure 5 is the value of f at the right endpoint of open bracket 2, open bracket 1 and 2, close bracket, that is f of 2 equals a sub 2. So comparing the areas of the shaded rectangles with the area under y equals f of x, from 1 to n, we see that equation 4, a sub 2 plus a sub 3 plus all the way through to a sub n is less than or equal to the integral from 1 to n of f of x dx. Notice that this inequality depends on the fact that f is decreasing. See figure 5. It is graph y equals f of x. And see figure 6. Same graph. But at the end is a sub n minus 1. Anyway, back to the text. Likewise, figure 6 shows that definition 5, the integral from 1 to n of f of x dx is less than or equal to a sub 1 plus a sub 2 plus ellipsis through a sub n minus 1. Number 1, if the integral from 1 to infinity of f of x dx is convergent, then equation 4 gives the sum from I equals 2 to n of a sub I is less than or equal to the integral from 1 to n of f of x dx is less than or equal to this integral from 1 to infinity of f of x dx, since f of x is greater than or equal to 0. Therefore, s sub n equals a sub 1 plus the sum from I equals 2 to n of a sub I is less than or equal to a sub 1 plus the integral from 1 to infinity of f of x dx equals big M. Say, since s sub n is less than or equal to m, for all n, the sequence open bracket s sub n close bracket is bounded above. So s sub n plus 1 equals s sub n plus a sub n plus 1 is greater than or equal to s sub n. Since a sub n plus 1 equals f of n plus 1 is greater than or equal to 0, thus open bracket s sub n close bracket is an increasing bounded sequence so that it is convergent by the monotonic sequence theorem, open 11.1.12 closed. This means that the sum of a sub n is convergent. Number 2. If the integral from 1 to infinity of f of x dx is divergent, then the integral from 1 to n of f of x dx approaches infinity as n approaches infinity because f of x is greater than or equal to 0. But equation 5, or definition 5, gives the integral from 1 to n of f of x dx is less than or equal to the sum from I equals 1 to n minus 1 of a sub I equals s sub n minus 1. And so s sub n minus 1 approaches infinity. This implies that s sub n approaches infinity. And so the sum from a sub n diverges.